we still have the moments.
It's like the eye test. Yeah, can you read the title? Can you read the names? Can you read the co-authors? I mean, it's going to be better with the slides, of course. It's but still, I mean, I don't know. We'll see. Like everything is, yeah, like compressed, right? The big screen, then my screen is in it, and then the screen is inside of it. I don't know. Ah, I can do this. Well, we don't know if we can make it even bigger because it's like there's still margins, but looks like maybe not because of the aspect ratio. I may not allow it actually, because then some of it will be. I think it's probably the biggest. Yeah, I think it'll probably be okay. Yeah, people can move closer. Yes. Yeah. I'm not gonna have anything with this font.
Young people should be in the back, which is
Yes. Well, I'm not sure young people have good eyes to see far. I mean, I don't know. Some do, but I don't know. Huh? To see far? I mean, you know, like I started wearing glasses, you know, pretty much when I started my PhD. So by the time I finished, it was not good already. Now the problem is I cannot see far or close. Yes, exactly.
Okay. Hello, everyone. Bonjour, tout le monde. I'm again here to introduce one of these Chaire Aisenstadt lectures. I did an introduction a few days ago, so if you heard me speaking already, you'll know a part of what I have to say. The first part is that my name is Octave Cornea, and I'm a director of the Centre de Recherche Mathématiques. So it's very good to have you here, and I want to thank you for coming. And the Chaire Aisenstadt lectures are associated to our thematic semesters. We have generally 2 Chaire Aisenstadt chairs for each thematic semester. And each chair delivers 3 lectures, and one of them is for a general audience, and this is a lecture of today. And okay, so I want to say a word about this thematic semester. So these are sort of the flagship activities of the CRM. They consist of about 4 to 6 weekly, 1 week events, of conferences, of workshops, maybe also schools. And in fact, they require a lot of effort to set up. And I want to thank the organizers, the main organizers of this thematic semester. So Tim Hoheisel and Simone Brugiapaglia. And very good. So one particular thing I want to mention is that they were very heroic in deciding to set up this semester, because we always plan the semesters maybe 3 years ahead of time, maybe more. And they started to think about it just in the pandemic, when the pandemic was it was 2022. And in fact, we didn't know for sure if the institute will still exist at the end of the pandemic. We were also renewing all our grants, and at the same time, all of them. So we really didn't know if we'll still exist in 3 years. So of course, as participants, it's better that you did not know about that. And so in any case, I think it's a great success this semester, and I'm very glad to have it happening here. And also, I want to also thank my staff. So Virginie Leduc is a coordinator of activities for the CRM, and she's doing a marvelous job She also learned the job because she was kind of newish when in 2022, and she's doing a great job now. And there are also Marion, who's working with us, and Maeva also. And we have also this IT great help, Madid, who is kind of setting things up with us. And okay, with all these thanks, I think you'll have the opportunity to thank them more, maybe at some moment in towards the end of the semester. But now I pass to Courtney, who will introduce Katya, who will deliver her last lecture today, I think.
Yeah. Thank you all for coming, especially on this beautiful day outside. So it's my great pleasure to introduce Katya Scheinberg, who's a Coca-Cola Foundation Chair in the School of Industrial and Systems Engineering at Georgia Tech. Prior to joining Georgia Tech, she was a professor at Cornell and Lehigh University, where I actually first met her. I owe her quite a bit for where I am now. I don't even know, I'm now tenured.
Yes, you told me, yes.
So thank you for all your help. Katya's main research areas are related to developing practical algorithms and their theoretical analysis for various problems in continuous optimization, such as convex optimization, derivative-free optimization, machine learning, quadratic program, and many more. She's the recipient of numerous prizes, including Lagrange Prize from SIAM and MOS, the Farkas Prize from Informs Optimization Society, and the Outstanding Simulation Publication Award from Informs. So with my pleasure, I'll pass it to Katya. Thank you.
Okay, well, thank you so much. And it is really an honor to be giving these lecture series, and you know, it's especially impressed upon me when I'm walking here down to my office and you see pictures of people like Paul Seymour and Terence Tao. Now, he was probably 19 when he was here, but nevertheless, it's quite an amazing series. So thank you for having it and inviting me for this. Okay, so this is meant to be a general public lecture. I suspect most people here are actually familiar with optimization, but you know, it will not be a very high level lecture. It will be kind of technical, but also slightly philosophical, but it should be self-contained. So hopefully it will be, you know, accessible more or less. So this is something that I've been interested in. Yes, okay, sorry. This is just on my computer. This is something that I've been interested in for a while, this kind of concepts of noisy oracles in optimization. And this thing is not working for some reason.
Click on the slide, Chaire. Just click on the slide before.
Okay.
Yes, click. Yes, no.
Nope. It was working before. It would be good for it to work because I have a lot of clicking to go through. I can stand here, of course, but yeah, I don't know. I mean, it was working and it's on. I can turn it off and on. Okay, something. This is so strange.
Does it move with arrows? You can try with that.
Keyboard arrows? Oh, no, it's not even working with that. Oh, now.
Oh, there
Okay, now, yes.
Okay.
Okay.
That work?
Yes.
Okay, it's working.
Yes. What?
I know why it's.
It's doing something very strange.
Is it like full screen mode? Is that?
Yeah.
Wait, can you put it in?
Okay. Yes, excellent. Okay. Okay. Right. So what we're going to talk about? We're going to talk about basic methods of unconstrained optimization. So I have a function phi that I want to optimize without any constraints. Many things carry over with constraints, but we'll just focus on the basic thing. And what I call the first order oracle is something basically you all probably know. If I want to optimize a function, what I want is to compute its gradient. So somebody gives me a function, I tell them, well, I'll optimize it only if you are able to compute a gradient for me. I give you x, give me the gradient of phi, right? And then I know what to do. So I also will assume that my function is nice, and as nice basically as it gets for, well, as nice as it gets for optimization is convex. I'm not going to assume convexity. Lots of things I'll talk about apply to convex functions in a bit stronger terms, but I will just simply assume that the function is smooth. What does it mean function is smooth? It means its gradients are Lipschitz continuous. I included the slide just in case not everybody is familiar what Lipschitz smoothness is. Lipschitz smoothness is Lipschitz continuity of the gradient, defined basically as Lipschitz continuity is in mathematics. And here are the three pictures of functions. First one is not smooth at all. Second one is smooth with a constant 4. And the third one is smooth with a constant 0.2. So L is very important constant here. It is a constant of the Lipschitz gradient, of the gradient Lipschitz continuity. And that L, basically is just something, we're not going to focus too much on it, but it has to be there and it has to be finite. And it comes into complexity. Okay, so this is what we assume, just so that we set our expectations. Then what we usually do in this case, we use gradient descent. Gradient descent is going downhill, right, with certain step sizes. So if I pick a step size alpha, so this alpha is going to be very key object in what I talk about. If we pick a step size alpha and we step along the negative gradient direction, this defines a gradient descent with fixed step size. And the key observation which comes out of Lipschitz smoothness is that if this alpha is not very large, and it basically agrees with the curvature of the function, then the function on every step will decrease by this amount, the amount of alpha over 2 times the norm of gradient squared, right? This is what we call descent lemma. This descent lemma is everything. This is everything to my talk, and this is really everything for most of continuous optimization. It gives us all kinds of things. Here I just list the ones for non-convex case, or at least general case, not necessarily convex, but basically this tells us if we have this property, from that we can conclude that gradient has to go to 0. And gradient going to 0 is all we can hope for when we do optimization with first order information. Gradient goes to 0, great. It goes to 0 at a certain speed. So as I progress, as I make k iterations, the rate of decay of the gradient is roughly 1 over square root of alpha times k. That's called the rate. Then there's also complexity. These two things are very tightly connected. Complexity means how long does it take me, how long will it take me to get to epsilon gradient, right? To see epsilon gradient, or epsilon gradient to occur. I may not see it if I don't compute gradients accurately. But anyway, so this is your basic stuff, right? Basic stuff, basic gradient descent. This is what we know. And what we're going to talk about is what happens to it under noise. Okay, so I go to ChatGPT. I ask, give me a few images motivating inexact gradient computation in optimization applications, right? Because you need some motivation, otherwise you would just not be interested, right? Anyway, so this is the, what? What is this? Like, I don't get it. The first one doesn't even have a function. What is this? And then this is gradient. I mean, it means minimum, obviously, but like this is an exact gradient, like there's some random arrows. Like, this is just so weird. And this chess piece, like, and like, what is this? Anyway, so then I realized what is the best thing about ChatGPT and other LLMs is that it is totally okay to humiliate them in public. And it is very satisfying. So we'll do it. Okay, so sorry, motivation, I'll have to provide my own motivation. Okay, so this is an outline. I'm going to talk about deterministic and exact oracles. I'll define one in my way. I'll explain how it connects to what is out there. And I'll talk about how it reflects in the algorithm. Then I'll talk about stochastic oracles, and the same thing will repeat. And then at the very end, I will talk about this thing called probabilistic oracles, which is interesting but kind of much less commonly established. Okay, so deterministic first order oracles. Any questions before? No. Okay. Right. So oracle. What is an oracle? Again, it is basically a routine. I'm thinking about it like code or some procedure or whatever that in principle supplies me with the estimate of the gradient somehow. I understand it in a very broad sense, and you'll see that it's in some sense it can be understood in broad sense. So this G is somehow given. I don't have the exact gradient, but I have G. I have access to G in some form, and this G satisfies these properties. So the properties are basically the difference between G and the true gradient is bounded by two quantity with two constants. And this is very important in what I'm talking about, because so there's this absolute error and the relative error, right? So there's epsilon G. I call it epsilon deliberately because I kind of need it to be small to get anywhere. And then there's this other constant that multiplies the norm of the gradient. Okay, and it all comes at some cost. So in principle, I might make this epsilon and kappa smaller at higher cost. And this is often the case in applications. Okay. So the method I'm going to employ is essentially an exact gradient method. So I'm going to take fixed step size alpha, and I'm going to take a step in the direction of negative G. And the descent lemma now will look like this. And I hope it's possible to see because I know the screen is a little small. But basically, there is this decreasing part, which we had before, except for now it's multiplied by a constant 1 minus kappa G squared. So before we just had alpha over 2 for exact gradient, but now we have this extra term that is smaller than 1 if kappa G is less than 1. If kappa G is bigger than 1, then we don't have a decrease at all because this becomes negative, and so that's not good. So we need kappa G less than 1. And this derivation holds when alpha is less than 1 over L, just as in gradient descent. The step size can be exactly as in gradient descent. And then there's this extra term. And you can now see the reason I emphasize the difference between these two pieces of noise, because the first piece of noise is the one that is sitting in this term and adds to my trouble. In some sense, it does not let me reduce my function because it adds something. And this one reduces my function, but just a little bit slower if kappa G is not 0. So kappa G is 0, epsilon G is 0, I recover gradient descent, obviously. Okay, so what are the conclusions from this? The conclusions from this are that I cannot drive gradient to 0 because I cannot, this term is just not going to let me. But as long as this term is smaller than the gradient, and this is precisely the formula, so as long as the gradient is bigger than epsilon, which is bigger than epsilon G over square root, then it is basically, it's going to reduce. The function is going to reduce. So my gradient is going to go to any epsilon. It's going to reduce below any epsilon that is sufficiently large. So this is good to know because I know if I know my error in the gradient, I know, basically where I'm going, right? I know what I can achieve and what I cannot achieve. And this is how fast I'm going to go there. So where I'm converging is epsilon G. How fast I'm converging is kappa G, right? These are the two different things. Okay, now I have visual, explanations, so to speak. So the red is the gradient. So I have these contours of a function, which you don't really see very well, but you probably don't need to. The red is the gradient. The blue is the approximate gradient. The circle around the tip of the gradient is exactly, so kappa G here is 0.1, epsilon G is 0. And you remember my bound is basically, it says that the norm between G and phi should be bounded by this. So that's the radius. So the radius is defined, kappa G and epsilon G define the radius. Okay, so this is good. This is where the blue one can be anywhere. The tip of the blue one can be anywhere in that circle. Okay, so I add epsilon G. It essentially is the same as, so if epsilon G is small compared to the gradient, and this is, I can derive the formula for you, but instead of show it visually, you can actually reformulate it as just having larger kappa g and skipping epsilon g, making it 0. So it is, again, the same thing. I need to be in a circle around the red arrow, right? Just a little larger circle. So this is fine. Now here is when kappa g is 0.9. So we know it has to be less than 1. If it's 0.9, you know, the circle is quite a bit larger. Epsilon g is 0 here. So, you know, my gradient estimation can vary a little bit more. This is when kappa g is bigger than 1. And it's very hard to see, but the blue thing is now sticking in the opposite direction. So it is no longer giving me direction that is aligned with the gradient. I cannot step and get ascent, or descent rather, if I step in a negative. Actually, this, I think I'm, no, this is right. This is pointing me, sorry, I didn't explain, but these are contours of a function. This is all going uphill, and I will keep on pointing uphill just to be consistent. So we always know we're going downhill, but this is always pointing uphill. It is good for the stock. Okay, so basically, kappa bigger than 1, not good. Visually very clear. And finally, epsilon g, so this is again, yeah, I'm somewhere close to where the gradient is 0. And I happen to be next to a saddle point actually here, but, or maybe local maximum. The gradient is small, and so my epsilon g is now going to really interfere and not allow me to have, or it's basically, it's preventing me from having a good gradient approximation. So all I'm trying to say here, it's like visually very clear that this epsilon g contribution is all about what size of the gradient I can possibly deal with, after which I'm stuck. And kappa g is all about basically, you know, being a descent direction. And I'm going to talk about this a bit more. First, I'm going to, so this is the pictures, the motivating, you know, now I'm going to talk about 2 cases first of very specific gradient computation that you probably are all familiar with, and that we can easily analyze it. They will give us the error that, you know, falls into this category. So the first one is finite differences. I'm not going to dwell on it too much. So if you don't have the actual gradient differentiation process, you can apply finite differences to compute your function. And if you have a noisy function, which is important because very often, you know, there's noise in the function. So I'm assuming my function estimate. So my function is phi, but f is what I get. So I also have a 0th order oracle that is also inexact. And I'm using that to construct a first order oracle, right? So I have function computation, and I'm using to construct first order oracle. I'm doing it by finite differences. So I can do the analysis. I'm going to skip that part. But the important part is that through this analysis, I'm going to find the bound on the norm of the difference, which is exactly what I was looking for. And this bound has basically 2 pieces. One piece comes from the fact that I'm doing finite differences. The other comes from the fact that I have noise, and they have the same element there, the step, finite difference step, which appears in top and bottom, and I have to balance the 2. So there is some noise issue in a sense that I have to pick this delta really carefully in order to minimize that error, okay? This is going to be important in some sense because it's going to come up slightly differently in stochastic case, and that's the interesting part. But right now it's kind of straightforward. It's just something fixed. You fix the delta. The best delta you pick is going to be, you know, the one that balances these 2 terms, and then you just have a noisy oracle. So here I start with some function values. I compute the noisy gradient. And this noisy gradient only has relative error, only epsilon g. There is no kappa g, which means that I have basically gradient descent, convergence same rate, everything until I hit the limit of how small my gradient can be, which is defined by the error, which is defined by the function error, right? So the function error tells me how well I can do in terms of this algorithm, okay? It's all very, very basic, probably very familiar. Okay, these are pictures of, yeah, you know what, let's skip. Okay, so next, is not something you think about as the first order oracle exactly, but maybe you do. And it comes from coordinate descent. So here I have the gradient again, and I'm going to look at its coordinates. And at least one of its coordinates, at least the largest one, is going to, well, this is a very hand-wavy statement right now, but you can see I have two coordinates of the gradient, right? So I just decompose it. And I drew this circle of a certain radius around the center, and the one pointing down is within the circle. So it is an inexact oracle with the sufficiently large radius, basically, around the phi. So I can find these constants. And then the other one is not, but they're both descent directions. So we'll get to that in a second. So if I actually derive the formula, so what I've described here is I pick S largest components of the gradient. I can analyze the difference between G and nabla phi, and I get this. So now I have the oracle without epsilon G. So there's no error epsilon G, but there is error kappa G piece. There is relative error, which means I will converge to optimality. Coordinate descent converges to optimal solutions. We all know that. The rate of convergence is going to be slower, though, because now I have this kappa G. How much slower? Okay, S is the number of components. Say S is 1. If S is 1, I just do one coordinate at a time. Then kappa G squared is n minus 1 over n. Okay, it's close to 1. That's not very good. 1 minus kappa G squared is going to give us basically this rate of convergence. So I will converge to stationary point, but I will do so in n over s more iterations than gradient. The gradient descent converges in 1 over alpha epsilon square. This thing converges in n times over s, that. Now, each iteration could be, it depends on what I'm doing and how I'm doing it, but could be s times cheaper. But I have s times more of those. Okay, so this is no free lunch result. There are, of course, more subtle things about things like coordinate descent, such as Lipschitz constants and step sizes, but you have to be careful. At least directly, you're not saving anything. And it really comes with the analysis of the properties of the oracles versus the oracle cost. Okay? Any questions about this? Okay, so especially those of you who have seen optimization in even like some basic gradient course, you kind of know that descent is what you care about, right? Again, I call it descent, and I'm drawing ascent directions, but just to be consistent. So we kind of think of it as descent direction when we take the negative of that. So ultimately, in many papers and books and whatever, you will say, okay, well, I need the angle between the gradient and my whatever estimator to be somehow acute, right? So presumably I have like this whole half space of available gradients, but I can't quite pick anything there because, you know, I need to make sure that my angle is at least stays strictly positive, bounded away from 0. So at least I have to be in this wedge, okay? But there's more. I also have to, I cannot take arbitrarily large, although it can be very large, but I cannot take arbitrarily large steps. And in fact, actually, the large part is not even important. I cannot take arbitrarily small vectors, because arbitrarily small g's, even if they are aligned along the gradient, if they're very small, the progress is going to be tiny, and I'm not going to guarantee any convergence. So now where I need to be is in this wedge, but with a cutout. So it's like this wedge of the annulus, right? So cut out center and inside the big circle. Okay. So now I claim that I can always draw a circle around the red arrow, okay, with kappa G. I don't need epsilon G here. Kappa G less than 1, that will fit like this, okay? So now, what are we saying? So we're saying that, okay, my definition of the oracle says things need to be inside the magenta circle. The kind of traditional definition of descent that people use often, you have to be in that wedge. That wedge is bigger, right? People say, oh, it's a bigger wedge, so it's better, right? You have more gradients to play with. It's easier to find things in this bigger, in the wedge than in the circle. But if you look at the picture, anything in that wedge, you can just scale down and end up in the circle. That's why I drew it like this. So here's the picture. If something is in the wedge but not in the circle, I just can scale it down. And here is the exact formula. So this is the definition of the condition that is often used in literature. So you have to have an inner product to be at least beta 1 with betas being positive times the gradient norm squared, and then it cannot be too large. And then it implies the cosine is positive, and you can analyze this directly. You can analyze this method directly and get a descent lemma, which looks like this. If alpha is small enough, and small enough is this beta 1 over beta 2 squared, blah, 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 then the decrease is proportional to what we had before times beta 1, right? So this is the decrease we get with alpha sufficiently small. On the other hand, I can do this. I can just scale down that direction of descent as the one in the wedge. I scale it down. I end up in the circle with a kappa g defined by this. And then I plug it into my descent lemma that I had before, and I get exactly the same result. I'm not losing anything. It's exactly the same. I'm not gaining anything either. But the point is that my definition, I'm showing you that the definition of the oracle is actually ubiquitous in some sense. It gives you exactly the same result than any other definition that we know. Yeah.
Why did you need the angle between the gradient and the estimate to be greater than 0?
Because otherwise I just cannot progress, right? I mean, just visually, if I'm taking direction along negative gradient, right? Just think about it. You're like standing on a mountain. The gradient tells you should go this way. I mean, gradient's pointing uphill, but I'm going negative gradient, right? If I go anywhere that is not acute angle with the gradient, then I will be going uphill, right? Yeah, that basically it works out when you're doing the algebra here, but visually that's exactly what it is. So it's like this is this is conditioned from, I don't know, the 60s probably. Yeah. Okay, any other questions? Okay, a little bit more. So this is a little bit more maybe towards specialists. So quasi-Newton, I'm not going to talk about what quasi-Newton is, but basically a gradient descent by itself is usually not such a great method, and very often it is used by multiplying the gradient by some kind of a matrix, which is positive definite, and it basically helps with convergence speed. And the idea of this matrix is that it somehow resembles the Hessian. It can be the Hessian itself, then it would be Newton method, or it can be some approximation, then it's a quasi-Newton method. Okay, so it is well known that if I take a positive definite matrix and I multiply it by multiply gradient by it and I take the negative direction, it will be a descent direction, just as we just were talking about. It will be a direction in which I guarantee to reduce my function. So that's important. But now I don't have exact gradient. I have something that is not exact. Can I say something? Turns out, yes, these are a lot of formulas. Doesn't matter. The important thing is there is a very specific condition. Actually, there are multiple conditions. This seems to be the strongest right now, or rather strongest, weakest, the best. Condition which says that if my kappa g is something, and remember, I can always sweep epsilon g under the rug if I assume my gradient is big enough. So this is quite general. It's not strongest to assume that epsilon g is 0, but kappa g is where the whole kind of thing sits. So if kappa g is sufficiently small, let's put it that way, then I will have a descent direction. And what is sufficiently small is defined by the condition number of the matrix that I'm multiplying by. So if you're multiplying by identity, for example, then kappa b is 1, and then kappa g is less than 1. You recover the original result. If not, then, you know, And when you think about it geometrically, so this multiplication by a positive definite matrix rotates my vector. And so if my vector is already rotated with respect to the initial gradient, I'll rotate it some more. I cannot rotate it anywhere I want. I have to rotate it depending how much angle there already is to stay again with the acute angle. That's what it is. Okay. All right. Whew. Take a deep breath. Mm-hmm.
Latitude in the Hessian approximation, you can't explore the curvature as much as you could have done that.
Exactly, right. That's exactly right. Yes. So it's the relationship, or if you have control over your accuracy of the gradient approximation, you have to work so much harder, but then you can exploit your, yeah, exactly. Yep. Okay. Stochastic stuff. Right. So we now have a gradient that is computed, or rather the g, that is a vector, which is random and computed by some kind of stochastic procedure. There's a random variable involved there somewhere, and it spits out something that is random. So we can now talk about the bias and the variance of that random variable. And so the bias, so in ML, we are very used to saying gradients are unbiased, but actually there are plenty of gradients that are not unbiased. And we now know how to deal with the bias, because bias is basically exactly this constant or deterministic error. So this first term is now just basically on the bias of G, and it's exactly as it was before, and it's going to behave exactly as it did before. But now, in addition to the bias, we have the variance. And so the variance is also has two terms, and it's also very important. These two terms will have different effect. And the first one is the constant kind of term, and the second one is the relative term. And why is relative important? Because when the gradient goes to 0, these second terms, they go to 0, right? That's why they're so special. That's why we care about them. Okay, so here's a picture. It looks bad, but so this is, it's really a stochastic, whole bunch of stochastic gradients whose average is the green arrow, and the red arrow is basically what the true gradient is. And you can see that there's a little bit of bias between the green arrow and the red arrow, but it's not very large, but the variance is all over the place, right? But it will have, because it's variance, we'll see how it will have less effect. And in fact, okay, here is the descent lemma. And again, everything derives from that. So the descent lemma now has more terms. So it has the terms that it had before. And now it has the terms that come from the variance. So in front of the descent piece, the negative piece, we have alpha L sigma V squared, right? So the sigma V, which is piece of the variance, comes in there. And then in the positive term that kind of stops us from converging, we have alpha square L over 2 sigma C squared. So again, they've separated into two pieces. The one of the relative error goes into my decrease, speed of decrease, and the absolute error goes into basically like the barrier where I cannot push through, right? But why is it so different from, why is it so special, this variance, in comparison to deterministic error, is because both pieces are now multiplied by alpha. They have an extra alpha there, right? So deterministic error, the one that is on the bias, is here without alpha. Here it's with 1 alpha, and this piece also has 1 alpha here. But here I have alpha square, and here I have an extra alpha, which means that I can make alpha small and make these pieces small as I want, basically. It will cost me convergence rate. It will cost me because the smaller my step size is, the slower I converge, right? But I can make them small, and I can make progress. Okay. So I do need to make sure that alpha is smaller than this, for sure. There's no question about that. And then I can definitely converge to a gradient whose, converge to a value of the gradient which is bounded below by this quantity. And this quantity here, as you see, has these alphas. And again, if I make alpha smaller, I can converge to a better solution. Like if epsilon g and kappa g is 0, like in stochastic gradient descent in machine learning, no bias, then I will converge to the optimal solution by, or arbitrarily accurate solution by making alpha small enough. Okay? So in fact, I can, now, some of you had seen probably like Robbins-Monroe analysis and all this kind of analysis of stochastic gradient descent. And it goes different, like there, the alpha is not fixed. Alpha is progressively getting smaller, and you can do that analysis as well. But here, it's very easy to see that I can just pick, if I have epsilon in mind, all I need to do is to pick epsilon to be the smallest of these two values. And I'm sorry, this is kind of small here, but there are two different values. One is defined by sigma v and kappa g, these relative noise terms, and the other one is defined by epsilon and sigma c. And okay, this is under assumption epsilon g is not interfering. If it interferes, I cannot do anything. But if there is no epsilon g, if there is no actual like bias term, then I can make my alpha small enough. And now, if my sigma c is large, I will need to make alpha order of epsilon squared. And then I will converge, but my rate of convergence is going to be 1 over epsilon over 4, which is exactly what you get in the in stochastic gradient analysis. So you recover exactly those results in a very, very simple way just from this one descent lemma, which is why I like this so much. It's like really quite amazing. So just plug in things differently and you get what you want. Okay, so examples. Examples are machine learning, of course. Machine learning, you have expected risk minimization, you have some kind of a bound on the variance of the loss function of the gradient of the loss function, and it also often comes in two terms, the relative and the absolute, and then you take a mini batch and you average your gradients over the mini batch, and that gives you the variance of your gradient estimate. So your first order oracle now is just simply a mini batch gradient, right? Like everybody who's ever seen now machine learning algorithms or optimization algorithm would see that. Okay, so what do I want to emphasize here is that so the variance, the sigma terms, they come from the variance and they're divided by the mini batch size. The bigger the mini batch, the smaller the variance. So you can work harder and get more accurate solutions. We know that, right? This is a good point. But basically, the convergence theory tells us that the number of iterations that you need to converge to an epsilon stationary gradient will scale with 1 over the size of the mini batch. And the complexity per iteration will scale with the size of the mini batch. So overall, you're a wash and there's no free lunch, right? Again, obviously, we all know that it's not true that it doesn't matter what mini batch size you pick. People usually do careful mini batch tuning, but it usually is related to cache memory and some other issues that has nothing to do with algorithms. Okay, and again, another thing that I want to emphasize, so there is a very nice line of work where stochastic gradient descent is analyzed, so there's no bias here, right? It's analyzed under the case when the sigma c is considered to be 0 or small. And nice properties have been recovered for gradient descent. And basically, it was shown that stochastic gradient descent under these conditions behave kind of like deterministic one. And we are getting it right here. It is visible here. If sigma c is small, then we don't have this piece, and the convergence rate is 1 over epsilon square, which is exactly the same as gradient descent. You can apply this to convex functions and many other and accelerated algorithms and things like that. This is there are some papers that argue that this actually happens in neural networks due to overparameterization, that the sigma c is actually very small, and therefore that explains the success of stochastic gradient algorithms on these problems. Okay, next. Now we're going to go back to finite differences, but this time I'm going to take the noise that is stochastic. Okay, any questions? Yeah.
Totally makes sense. But if it's any difficulty, then intermediate when we pass the complexity off.
So
just a one step sound enough then.
So I'm, you know, so if I'm picking alpha fixed, then it just accumulates, right? It's like it's all the same. It's all the same analysis, essentially. I mean, you do expectation, of course, but yeah, I mean, with complexity bound, it is a little bit less common to do a complexity bound. Usually it's expected rate. I just want to show things, but you can do even the bound on the expected complexity using some martingale stuff. So it works, but I'm deliberately keeping alpha fixed, so it's easier. Okay, yeah.
Here in machine learning, you assume the Lipschitz. How can you, like, mostly when you go to higher parameters, they're not Lipschitz, or when you.
So I'm sorry, what are you talking about? Lipschitz, the L is Lipschitz?
Yeah, sometimes.
I'm not assuming that L is Lipschitz, actually.
But the L existed, right? So.
Oh, can take the gradient of the loss. Yes. Yeah.
Like when you, for instance, they train it in edge cases when they're dealing with integer training or floats. Like
Yes. Okay.
the edge cases, they don't actually have.
Okay. Okay.
But
Then
still this whole.
what holds?
This cheating works after iteration. They can still train the network.
But how do they compute the gradient?
That is what.
Okay. So I don't care about this. This is just a motivation. I care about this. Just give me any gradient computation. If you can guarantee some kind of a bound, then you can apply this analysis. That's all I'm saying. You can compute it any way you want, right? Yeah. Anyway, I mean, it's sure. I don't know, but that's a very good point. You compute your gradient, sit down and try to analyze what is the variance, right? And where it comes from, and what are the pieces of it? Like, is there constant variance, relative variance, and what does it mean for your algorithm? That is exactly what I'm trying to emphasize here. Yeah, I don't care where it comes from. So these are just examples. This is an example. Simulation optimization has existed for quite a few years, and basically this is what it boils down to if you don't have a gradient. Very often in simulation optimization you have some kind of gradient computation, but if you don't, you take two estimators of your function. Each estimator is by itself an unbiased, usually estimator, so we'll assume it's unbiased, but it has some kind of variance, and I'll assume this variance just has, you know, bound, because there's no point in talking about relative variance for functions as much. I do the same trick. I decompose whatever, then I take expectations. Again, we don't have to go through the details. The key point is that, again, I get these two pieces. I had two pieces before, but they were basically like, they were both contributing to the error. Now I have two pieces and they both contribute to the error, but differently. The first piece is the bias. It's actually the bias. It's the difference between the expected gradient and so it comes from the fact that I'm doing finite differences. So there is definitely a fixed error there. This is the variance. Okay, this piece is the variance. Okay, so we already know that variance behaves differently than just a deterministic error. So, and here there's just another little twist, but it's really cool, I think. You have two pieces of noise. I don't have any relative noise here. I have only absolute noise. I have the bias and I have the variance. And the bias is multiplied by delta, and the variance is is divided by delta. So if you recall, if I want to make the bias small, my variance will go large, right? Very classical trade-off between bias and variance. So you think it's kind of a problem, but it's not, because this variance gets multiplied by alpha. So if I make alpha small enough, then I can always make that term small enough. So now all I need to do is to make sure that alpha is not just small, but alpha over delta is small. Delta should go to 0. This way I can reduce my bias and actually converge to an arbitrarily good solution. I'm going to do it super slowly, but I can do it with picking alpha that is sufficiently small. And again, this is nothing new. People have been doing this in various, but like in simulation optimization, basically this technique has been used with different algorithms and now we have like this framework that just says this is what you do, and we even have rates and everything, and it's just very simple. Okay, some more stochastic. That gets difficult, right? You can throw in stochastic stuff. Okay, I'm just gonna go over this relatively quickly. What can you do? What more can you do? So this was finite differences, right? The finite differences requires me to compute the gradient estimate in every coordinate. But you can now also do this in a subspace. So I can compute random subspace gradients. If I compute, what does it mean, random subspace gradients? I take a random, and I have 4 different ways of generating directions: Gaussian directions, unisphere directions, several coordinates, or just orthogonal vectors. So I have S vectors in an n-dimensional space. So large dimensional space, pick 10 vectors, generate them randomly from some symmetric distribution, and basically project your gradient onto each of them individually and then aggregate them like this. This is a stochastic gradient estimate. Why is it good? Why would you do that? Well, various reasons, but if you want to make steps in subspaces, if you don't want to update the whole set of coordinates or whatever, if you just want to make steps in the subspaces, you will do this. And this is a stochastic gradient estimate which has no bias, which has no relative absolute noise, and it only has variance that is relative, which means that an algorithm applied to this stochastic gradient converges, gradient descent converges as if it's deterministic. A little bit slower, but essentially as if it's deterministic. So this is an example of stochastic gradient, which has all the good properties, and you don't need to make alpha go to 0 or anything like that. Okay? Now you can put the previous 2 things together. You can take random directions to finite differences on top of that. And this is when we're going to get all pieces, everything, the bias, the 2 terms of, just 1 term of the bias, epsilon g, not kappa g, the bias, the absolute variance, and the relative variance. They're all together, and you can play with them all you want, and you can, manipulate them, and now you know basically what to do in terms of convergence. So it's a lot of formulas. You can probably see them, especially from the back. So it doesn't matter. Okay. Right. Okay, so this part is going to be short. So I'm going to motivate it and then just basically tell you that there's a bunch of these things that are really interesting. So the way I'll motivate it is by going back to stochastic gradients in machine learning. So I have the same situation. I have gradients. I assume I have the gradients somehow, individual sample gradients. I can compute them, and I can aggregate them into mini batches. And now I have several mini batches, not 1, but several, 5. I have 5 mini batches somehow. I computed 5 mini batches. But out of these 5 mini batches, 2 are corrupt for some reason, right? Somehow. So if I average them out, so this is the picture, right? I have 3 points. I'm assuming my average is 0 just for scaling. So I have 3 good gradient mini batches and 2 bad ones. If I average them out, as I normally would do, I will get garbage, and that's not good. There is robust estimators for that. There's many different types, but the computable ones are the 2 I list here. One is geometric median, which is basically, well, I'll show you in a second what it is. And then the other one is this radius-based estimator. So geometric median is generalization of a median. You just compute a vector that minimizes the distance to all 5 gradients. And the sort of very well-known estimator, but with unknown name, which I learned from Dima, but it's actually from Nemirovsky and Yudin book. It's basically you select one of these 5 points that has the smallest radius of the ball that contains more than half of the points. That's what it is. But the picture is worth definitely 1,000 words here. You can very easily see that both of these robust estimators are clearly not affected too much by the outliers, and they have very nice properties. Okay, so this is all good. And now the question is, where do these mini batches come from and how do they get corrupted? So there are 2 settings. One setting is very well studied in the literature, where they come from 5 different machines, where the data is stored, and the corrupted pieces that come from a particular machine which is corrupted. Somehow the data in one of the machines is corrupted or something, right? So you have either kind of pure mini batches or corrupted mini batches, and then everything kind of works, and you still have to work, but you could derive the bound on expected difference between what you estimated, this first order oracle, and the true gradient. And the bound is proportional to the variance of your original function, whatever, your mini batch, basically, the pure mini batch. However, this bound on the variance, this is not the bound on the variance. This is variance. This is not variance. This can be bias or the variance. Depending on the situation, this error can be all bias. It is not so easy, but you can still do it. The worst case comes in a different situation when it's all on one machine. So you have data on one machine, and it gets corrupted with some probability. And now what you do is this median of mean approach, when you select several mini batches and then you try to aggregate them using robust statistics, but bounding that baby is really difficult. We've been trying to do that. But what you can do is you can bound it in probability. You cannot bound expectation of this thing, but you can bound it in probability, which means that, so bounding the expectation means that you cannot have arbitrarily bad error, or at least you know the probability of that, right, somehow. But it's hard. So this is the probabilistic oracle, which is very strong or very powerful, but it's much, of course, harder to deal with as an algorithm. And I stated in general terms, no longer even for gradients because it exists for other things, but basically it is the same as I had before. I have an error which is bounded by something. It's basically like a deterministic oracle, but now I allow it to fail with some probability. So think of my deterministic oracle and just say, okay, but now it only holds with some probability. Yep, I'm done, basically. So this is, these oracles are, as I said, they're super interesting. You can pick them up in if you start thinking in these terms, you are open to so many different approximations of Hessians, function values, gradients. So I just gave you some example. There's eigenvalue of subsampled Hessians. Is another oracle. You can estimate sparse gradients with random sampling, whatever. Using them in an algorithm is hard. It's been ongoing work, and hopefully it will continue. And basically, the conclusion of all of this is that it's good to kind of categorize noise and know what we understand about it in terms of algorithms. I only talked about basic gradient descent, but a lot of things can be already seen from it, and a lot of things extend to somewhat more interesting concept. And then we will be able to better match algorithms and oracles if we understand how they interact in terms of these noise assumptions and have better convergence properties. Because I owed ChatGPT something, so stochastic and noisy oracles, snoracles. So this is, I mean, this is what I want to call them, but I think it's a little. So I asked ChatGPT to give me some ideas of oracles that make some sense, but make different types of errors. And this is what it came up with. Was very excited, much more excited than my inexact gradient examples from industry. Okay, thank you.
Thank you. Are there any questions? Oh, hold on. I'm gonna try and get it back. Thank you.
It's to give you mic, but okay. You were mentioning about this median of means, and you were talking about outlier. Like, how do you? I mean, it's general question. Like, how do you distinguish between a point that is a part of your distribution or it's an outlier? You know.
So you don't need to distinguish with these robust estimators. That's the whole point, right? You don't need to, right? You just like if you don't have these with these robust estimators, basically, if you have several mini batches and less than half of them are corrupt, then it's just automatically not going to. It doesn't have to detect which ones are corrupt. That's the whole point.
Okay.
Yeah. So I mean, there are other kinds of robust methods that try to distinguish, but we don't need to do that. Yeah.
Sorry, on the same topic, are you using the gradients themselves or the function values?
For for robust one?
Yeah.
Gradient themselves. I mean, this is a whole other thing. Like what is a corruption, right? How does a corruption even happen? So at first we were doing examples on like take just compute the gradients from a standard model and then just make corrupt gradients like horrible, just multiply them by -20 or something, right? Sure, okay, but that's really too easy, right? What kind of corruption would trigger that? So then we started messing with the data specifically. So you have, I don't know, MNIST data and you switch digits labels, right? How does that affect? I mean, how to corrupt things is a whole other, field of study, in fact. I mean, lots of people are doing that, but yeah, we're just corrupting something and then just computing the gradients as we normally would.
Thank you, Katya, for the presentation. I have just a question between the assumption when you use actually the expectation and the other one with the probabilistic one. So in the bound one, it was like fully linear, which the probabilistic one, but the other one, there was the norm of the gradient was power to 2, which is much stronger.
Sorry.
So the oracle is you have. So like if the model is fully linear, it satisfies this.
Yes.
But the other one, it's not like really fully linear model in expectation. It has some power. I think the norm of the gradient was power to 2. You had.
Well, it doesn't matter. I just squared the whole thing. I square. So it's a good point. We've been struggling quite a lot with whether put squares or not. Just because the math is easier, but here is my stochastic oracle. Everything is squared, but it doesn't matter. In fact,
it's okay.
In fact, if I have this on the squares, I can just remove the squares and it still hold. This inequality with squares implies the same inequality without squares.
Okay. I can see that.
What you're talking about fully linear is a much more subtle thing, right? Because it's in a region.
Exactly. Yeah.
It's a very interesting interplay between So like you can just ignore this piece here and just think of epsilon g is the condition on the whatever fully linear, but you can also use the fact that it's that there are two pieces. Yeah.
Thank you.
Yeah. Right.
So can you convert the stochastic oracle to a probabilistic oracle with like Chebyshev or Markov
Yes,
inequalities?
absolutely,
Okay, okay.
absolutely,
And
yes.
is there any benefit to that?
No,
Okay, but then if you had a distribution where you knew more than Chebyshev, maybe there is a benefit.
so, I mean, so far, the algorithms we develop based on probabilistic oracles are really suffer from the fact that you don't know what happens if the oracle fails, right? I mean, Courtney knows she suffered a lot through through the line search that we did, right? So trust region is not so bad, but the line search is worse. So the problem there, the key thing you need there is to ensure that in expectation you get some reduction. You basically want a descent lemma of some form, right? But if you allow your gradient to be arbitrarily bad, you can shoot off on like this, even once in a while, a very bad gradient can completely undo your progress. So you have to do something else. So we were doing line search with function values and preventing things from whatever. And then we had to put some extra condition on the function values, but we could deal with bad gradients. It's so far not as clean as it could be. Or I don't know, maybe it never can be clean, but at least it's definitely problematic.
Thanks.
Yeah.
So regarding the median of means, so one could solve a optimization problem where I formulate a median of means optimization so as to drop the effect of the outlier somehow. Or I could do at the level of my gradient based method where while computing the gradients, I'm trying to drop this outlier somehow through this median of means criteria.
Okay.
So is it like are these one or the same thing? Because I was confused when you were mentioning at the level of gradients that you are implementing this median of means and not at the level of like solving an optimization problem, which is a median of means estimation problem.
I'm not 100% sure I understand, because I mean, are you suggesting to first solve optimization problem multiple?
An optimization problem which is a median of means estimation, like in the sense that I know that there will be outliers and I want to minimize an objective such that there are some corrupt samples.
Yeah. This is what I guess that's what we're essentially doing. Yeah.
I can say Eastern squares, for example. If you do Eastern squared where you minimize 90% of the best clinical data at the outset, and then you pick the algorithm that solves that problem.
Yeah. Okay.
Yeah.
I mean, this is it's a completely different setting, right? I'm talking about if I have corrupt gradients.
Okay. Okay.
Are there any other questions? I also don't want to keep people from the wine, so, and the beautiful day out. So maybe if we have more questions, Katya will be around, and I think there's wine and cheese in the room. So please give another hand to Katya.
So what do I do now? Okay, I can. Yes, exactly.
It's a pretty interesting question. So it's the problem I think we do a lot.
Yeah.
So you have 1,000 data points.
Yeah.
And you're willing to fit 950 of them because there might be 50 outliers.
Yeah.
You can write it as, you've probably seen this, there's no top here.
So I